All right, good morning, everybody who's here. So in the last class, we were talking about implementing a queue using an array. And we got to this slide here. And so we were talking about the NQ and DQ implementations. And when we reach this situation here, where let me back up one slide. Okay, so when you have a queue that has only one element in it, if you DQ that queue, you end up back in the situation where front and back are pointing to different elements in the queue, and they're one apart, right? So one front is one in front of back, which is the same situation that we had when we had an empty queue, where front was 0 and back was -1. Okay, so I guess one of the questions that you can ask is this a reliable way to determine whether or not the queue is empty? And a related question is can you compute the size of the queue given just front and back, or can you compute it easily? And the answer is going to turn out to be no, which is why we have to keep track of the size separate. One of the reasons why we want to keep track of the size separately. Right. So if you NQ again, right, front and back both point at the same value. Right. And if you keep on NQing, eventually back will end up at the end of the array. So we're now at the situation where we've got 11 elements in the queue, 10 elements in the queue, 11. We have 11 elements in the queue. There's still space in the array to hold more elements, right? But if we simply increment back by 1, we're going to fall off the end of the array, right? We're going to end up with back being 16, which is not a valid array index. So when we reach this situation here, you've got to make back wrap around back to 0. Because there's still room in the queue. So we want to use up the unused, there's still room in the array, sorry. We want to use up the unused space in the array. And so the only way we can do this, well, there's a couple ways you could do this. You either wrap back around to the front, or you take all of the elements in the queue and you shuffle them forward, in this case, 5 positions. Right. So back in the situation here, you could move the elements from indexes 5 to 15 forward 5 positions. And that would also work. The problem with doing it this way is that you have to now move up to n-1 elements in the queue forward, right? So that's an ON operation, which we would like to avoid. So instead, we're going to wrap the back value. We're going to wrap back around to the front of the queue. And then you keep on going, right? So 4 more in queue operations. Back is now we're now in the situation where, again, back is 1 for front, which is the same situation that we're in when we have an empty queue. Right? But now we have a full queue. And so this shows you that you can't, just by having back in front, you can't determine the actual number of elements in the queue. Right? The queue could be empty. It could be full. Also, the fact that you have to wrap around means that you can't just subtract front and back. And look at the difference to determine how many elements are in the queue. You have to take into account the fact that back may have wrapped around to the front of the queue again. So now if you keep on going, so if I now DQ everything, front starts to march to the right. Right? And eventually front reaches the last position of the array. So if you DQ again, if you DQ again, we're going to do the same thing with front. We're going to make it come around to the front of the array again. Right, so front wraps as well. So every time you're NQing or DQing, you have to consider whether or not you're going to wrap front or back. And so if you draw the queue in a different way, it turns out what we've implemented here is what's called a circular queue. This slide, so this slide corresponds to the queue that's in this state here. Okay. So we've got front and back. Right, all I've done is I've wrapped the array around so that it joins itself at the back. Right, so the front and back are now joined. And now in this picture, front and back always move clockwise. Right, so every time you NQ, right, so I NQ something at the back, right, back is just going to rotate 1 position to the right clockwise. Right, so you're going to fill in that value. Every time you DQ, you're going to remove the element at front and then move front 1 position clockwise. And so when you view this as a circular queue, front and back just continuously move around the circle in a clockwise direction. Okay, so what are the details when you implement this thing? It turns out it's not very hard. You just have to deal with the wrapping. If you can deal with the wrapping, everything else is pretty straightforward. Right? It looks more or less like a stack, except you've got front and back instead of top. Okay. So our generic queue, we might as well start out making it generic to begin with, because we know how to do that now. So our element type is going to be E. We're going to use an array of object to hold the elements. Right? Can't use an array of type E because Java won't let us do that. So we create an array of object instead. Object can hold any reference type, so that's great. Right. We've got a front and a back. So remember, front is the index of the element currently at the front of the queue. Back is the index of the element currently at the back of the queue. Size is the number of elements in the queue so that we don't have to do any quote unquote complicated calculation to determine the number of elements given front and back. Okay, no argument constructor. So this should make an empty queue. Right? You should always make the array. Back here again, remember, we don't have an array yet. We have a variable that can refer to an array. So make the array in the constructor. Right? That just has the default capacity, so 16 in this case. We should set front and back to some sensible values. The sensible values in this case, if we want to implement NQ and DQ simply, is to set front to 0, back to -1. Right. The fact that back is an invalid index is simply the consequence that we have an empty queue, and we need to set back to something. Finally, the number of elements in the queue is 0, so there's nothing in the queue. What about a copy constructor? So copy constructor is easy to implement as well. Right? There's a few different ways you can do this. The most straightforward way to do this is just to copy the state of the other array queue. Okay. So if you're going to copy the state of the other array queue, all you do is copy the fields of the other array queue, keeping in mind that a queue always owns its own array. Right? So in other words, you don't want two queues to share the same array. If they share the same array, then if you change one queue, the other queue also appears to change. Right? So we don't want to do that. So we have to copy the other array. Right? The easy way to copy an array in Java is to use arrays copy of. Front and back, those are just ints. So we just copy those values too, and size is another int. So we can just copy that value as well. And your copy constructor is now complete. The method front returns the first element of the queue without removing the element. So you can never look at the first element of the queue if it doesn't exist. So throw an exception if the queue is empty. Right. If there is something at the front of the queue, then we know where its location is. We have a field that stores its position in the array. Right, so that's just this dot front. So you simply go into the array, grab the element at this dot front. Now remember that array has type big O object. So you have to cast the element back to type E when you do this. When you write this in Eclipse, Eclipse is going to warn you that there's a unsafe cast happening here. Right. So when the compiler reads this, all that it sees is that you've got this array here of object and you're casting it to type E, right? What the compiler doesn't know is that the only way you're going to put things into the array is if you use, sorry, I have to jump ahead, is if you use NQ, right? So NQ always puts elements of type E into the array. So you know, as the implementer of the queue, that the stuff in the array are always elements of type E. The compiler doesn't know that. So it thinks that when you try to do this cast here, this might be unsafe, right? It might fail. And so you get a little warning, but the program will compile. Did you have a question? Yeah. Sorry, I guess I didn't explain that either. So the queue interface says that every queue has the methods front, back, NQ, DQ, and so on and so on and so forth. So when a class implements an interface, you can think of that as overriding the methods from the interface, even though the interface doesn't provide an implementation. If you put the @override in, the compiler will actually check if this is in fact the method that came from the interface. So it's there as a safety, a simple safety precaution for you, or for the programmer, sorry. Back is similar to front, right? So it's the exact same thing, except you're going to return the element at this back. DQ is just the simple DQ operation that was described in the slides from last class. Right? So to DQ the element from the queue, you're going to remember what is currently at the front of the queue. right? I need to remember this because I'm going to null out this value in just a moment. Okay. So the next step is whatever is currently at the front of the queue, I'm going to set that array element to null, right? And I now want to move front one position clockwise, right? So if you just had a plain old array and you weren't worried about falling off the end, right? You would just write this front equals this front plus 1, right? Now we want to make sure that if we fall off the end of the array, we want to wrap back to 0, right? So that's what the remainder operator is for, right? Your new value of front, you add 1 to front, and then you divide by the length of the array, right? And take the remainder. Okay. So this front plus 1 is equal to the length of the array. We know that you've fallen off the back of the array. We want to go back to index 0, right? So that's the length of the array divided by the length of the array, which is 1 and has a 0 remainder, right? So that takes care of the wrapping for us. Finally, decrease the number of elements in the queue, and then return the element. Right. Again, when you write this, the compiler is going to warn you that this is perhaps unsafe. It's not. Right. You know for a fact that everything in the queue or everything in our array is in fact of type E. So that we know the programmer knows this is safe. The compiler doesn't. All right. So the only other issue we have to deal with is in NQ. You might have to resize the array. And because of the way that we're storing the elements in the array, where the front element is not necessarily at index 0, so there might be null values at the front of the array, means that when you resize the array, when you copy the old array, you have to pay attention to how you're doing it. Right. So here is an example of a full queue. Right. So this queue is full. All the array locations are occupied by a string, right? The first element of the queue is the F. The last element of the queue is the U, right? Now, if I simply naively make a new array and copy the elements into the new array, you end up with the picture at the bottom, right? So in the bottom picture, all I've done is copied each element from index 0 up to 15 into the new array. Right. So this is what would happen if you used arrays copy of. Right. We're going to copy the value of front and back and size as well. Right. And now you can see the problem over here. Right. Because the array is now larger, we've expanded the size of the array. When you get to element 15 of the new array, right, there's still space in the array. Right. And so when you try to NQ at this point, when front or back gets here. So when you try to NQ, you're going to go to the next element instead of wrapping around to the other end of the queue. Sorry, instead of dequeuing here. So if you dequeue the P, that's fine, but front's going to move to the next position in the array, and there's nothing there. Right. And so what you need to do is there's a few things you could do. Right. So one way to correctly copy the elements from the old array into the new array, right, is to unwind the queue, right? So instead of having front be here, right, when you copy the elements, copy front to position 0, copy the next one to position 2, and so on and so on and so forth, right? So when you do that, back ends up over here, and now you have a correctly formatted queue, right? So that's one way to do it, right? And so if you do it this way, front is at position 0 of the array, and back is at the last element of the array. Right, and everything is now going to work fine. The other way to do this is to instead, so you can copy from front into here, right? Copy the next element into here, right? But when you get to the last element of the array, so we copy the P into here. When you copy the other elements, you make sure you put them at the end. Right? So Q ends up going to position 16. The R ends up going to position 17. Right, back ends up at what would it be 16, 17, 18, 19, 20. So back would be over here, right? And you would have a bunch of nulls at the front of the array. So that would be fine too. They both accomplish the same thing. Right. So I'm going to implement it this way. Right. So now you're in the situation where you can't use arrays copy of, or you can, but then you have to move the elements around. Right. So now we have to do it manually. So back to the old way of doing this, right? Make a new array. Make sure it's some multiple of the old array length, right? Where the multiple is bigger than 1. Now copy the elements from the old array into the new array, right? So when you write the loop, the thing to remember here is to remember exactly what is I an index for, right? So for our purposes, it's going to be an index for the destination array, right? So I will always be the index into the new array, right? So I can write temp I here because temp is my new array, right? Now you have to remember, so what is the source index equal to, right? So the source index in our case is going to start at front, right? So I have to add front to I. Right? So there's this front plus I, right? But now also remember that the index might wrap around to the front of the array. Right? So for front, when we get to 15, we want the next value of front to be 0. So again, you have to compute the remainder after dividing by the length of the original array. Right? And so all your calculations with the indexes, you always take into account the fact that the indexes might wrap. It's easy to do that, right? You just take the remainder with the length of the array, and that always gives you the correct index. Right? So once I've copied my array over, I can set my field inside the queue to point to the new array. Right? Front is now 0 and back is now size -1. Oops, sorry. Right? So front is now 0. Back is now equal to the size of the queue -1. Right? -1 because we're 0. We have a 0-based index. Right? Finally, go ahead and add the element to the end of the queue. So if we have space in the array, we can just jump to this part here, right? If we don't have space in the array, we do all of this, and then we go ahead and update the queue, right? So we move back 1 position to the right. Again, it might wrap, so add 1 and then take the remainder after dividing by the length. Set the element at the new back index and add 1 to the size. Right. So the only thing you have to watch out for is the expanding the size of the array here. Okay, so once you've got the basic queue methods implemented, so everything that's in the interface, you might want to consider adding extra methods to the class. Right. So this is a Java class after all. There's lots of other, well, there's some other methods that most Java users are going to want to use. Right, they're going to want a toString. They're going to want equals. If you have equals, you need hash code, right? Hash code is actually tricky. So that's another one that you might consider trying to implement. Hash code is very tricky in this case. You have equals and you have, so equals is also tricky a little bit. And then the copy constructor is an interesting one, right? So if our normal copy constructor would be arrayQ, and then you'd have arrayQ inside as your parameter, right? And so that's the one we implemented back here, right? I think we did that. Yes, here, right? So there's our copy constructor. So that lets an arrayQ, that lets you copy an existing arrayQ, right? And produce or initialize a new arrayQ. Now remember, we've got this queue interface, right? All queues have the same basic set of operations. And so it ought to be possible to copy another queue, right? So initialize this queue, initialize an array queue, so by copying the elements out of another queue, right? Now, when you do this, you have to remember that you're working with the interface, right? You're not working with the class anymore. So the only methods that you can use in this copy constructor are the ones that come from the queue interface, right? You don't know that this queue is an array queue. It could be something else. Right? Maybe it's a queue that's implemented using linked nodes. Maybe it's a queue implemented using a list or something else. Right. Furthermore, in this constructor, you don't want to modify the other queue. Right. Unfortunately, Java doesn't have a way to indicate this. Right. In C, you've got const. Right. So at least you can sort of suggest to the user that you're not going to modify the other thing. Right. Java doesn't have any notion of const. So unfortunately, there's no way for you to just look at this constructor and say, oh, it's not going to modify the other queue, right? But if you're copying someone else's queue, you probably shouldn't modify their queue, right? And so that's the trick here. How do you implement this constructor? without permanently modifying the other queue and still being able to initialize the elements of your array queue. So that's worth considering. Equals is tricky a little bit because if you define equals as being two queues are equal if they have the same number of elements and if they have the order of the elements is the same, you have to take into account the fact that you can have two array queues where the elements are rotated relative to one another. Right? So in other words, in your first queue, your first element might be at index 0, but in your second queue, your first element might be at index 12 or something else. Right? But they are equal. They have the same sequence of elements. So if you're going to try to implement equals where AQ, oh, sorry, there's actually another one. So if you're going to try to implement equals where you want to test if an array queue is equal to another array queue, right, that has a little bit of extra complication to it. Right. It gets worse. So if you wanted to compare if a queue is equal to another queue, or if an array queue is equal to another queue, right? That also complicates things, right? So if you can have an array queue be equal to, say, a queue implemented using a linked list, right? Inside equals, right? You're going to cast your other object to a queue, but now you don't get the advantage of knowing that the other queue is an array, has an array inside of it, right? All that you know is that the other queue has an NQ, DQ size and size operation. And so implementing equals now becomes tricky because you don't want to modify the incoming queue either. Right? If someone's asking you to test if two queues are equal, right, you probably don't want to modify the second queue, right, or the first queue for that matter, right? You don't want to modify either queue. You just want to test whether they're equal, right? And so that becomes tricky, right? If equals is tricky, then hash code is also tricky. And so I'll leave you to puzzle out or to at least think about how you might implement these methods, right? It's possible to do. You just have to figure out exactly what it is you need to do. All right. So I'm pretty sure we're going to finish all of the lecture material early, like maybe even a week and a half early. So I'm going to post a message on OnQ explaining what the plan is moving forward. All right, so if we have, we've got a stack with an array, we've got a stack with a list, we've got a stack with linked nodes, we've got a queue with a list, we've got a queue with an array. We might as well make a queue with linked nodes. Right. Again, this is probably more or less a review for most of you, right? Given that you've taken data structures already. Right. So if you're happy with the stack implemented with a bunch of nodes, you should be happy with a queue being implemented with a bunch of nodes as well. There's only one difference, right? In a stack, when you take something out of the stack, you remove the last element, right? In a queue, you're going to remove the first element, right? Similarly, so when you add to a queue, you're adding at the end. So that's the same as adding within a stack, right? In a stack that's implemented with nodes. So the only real difference is your nodes are added at the front. Nodes are added. Oh, sorry. In a queue, your nodes are added at the end. So this is what a stack looks like when you implement it with a bunch of nodes, right? Stack of size 1 just has one node in it, right? You push another element into the stack, then you add at the front, right? You push another element, again, you add at the front. With a queue, it's the opposite. You add at the back. Right? So in a queue, there's another difference here. In a stack, you never have a reference to the bottom element, right? Because you don't care, right, where the bottom element is, right? All you care about is where's the top element, right? Because everything that happens in a stack happens at the top. In a queue, you do care where the back element is, because when you NQ, you NQ at the back, right? And when you DQ, you DQ at the front. So you need to keep track of where is the front and the back node of a queue at all times, right? And this complicates things a little bit as well. So when you NQ, we're going to add an element at the back, right? You NQ again, you're going to add another element at the back, right? When you DQ, the elements will come off at the front. All right, so what does this look like? So it looks exactly like a stack, right? So instead of linked stack, you've got linked queue. right? Just like stack, you've got the number of nodes in the stack, in the queue, sorry. Right, now instead of top, you've got front and back, right? And these are both references to a node, right? I don't think we did we do a generic? We didn't do a generic stack implemented using nodes. So this is going to be, if you were to do a generic stack implementing using nodes, it would look exactly like this, right? So notice now, right, the node class itself becomes generic as well. Right? So in the previous example, node was not generic. It always held a reference to a string, I think, or an int, one of the two, right? Now our queue is generic. So our element type that's in the node is also generic. Right, so now our node class, which is going to be nested just like in the stack, also becomes generic. Right, so now it's a node where the element type is of type E. Right. That doesn't really change anything, right? All you do is you change the element type to E here. Right, your next link is now a generic node, right? It's a node that refers to a node that holds an element of type E. Right, your constructor changes, right? Instead of the elem being an int or a string, I don't remember which, right? It now becomes of type E, right? And your next node becomes a reference to a node whose element type is also E, right? So the changes here are pretty small to change it to a generic node. Okay, what does the no argument constructor look like? So the size of the queue is 0, right? There is no front or back node, so the queue's empty. So that's easy. Front is easy. We have a reference to the first node, right? So I can just return the element sitting in the first node. Right? If the queue is empty, I can't look. You can't look at the front node, right? So you throw an exception. Back is also easy, right? We've got a reference to the back node, so we can just return this back.elem. Right? So enqueue and dequeue are the only quote unquote tricky methods in this class, right? So to enqueue an element, you're going to make a new node, right? So remember, we're going to add at the back of the sequence, right? So we make a new node. We're going to store that elem in the node, right? We're going to add this node to the end of the sequence, right? So there's nothing after the new node. So we can set its next field to null, right? And now you've got some special cases. Let's go back to the picture here, right? So when you enqueue into an empty node, so remember, when we're implementing the queue, we have to keep track of both front and back. Right. So if you have an empty queue, there is no front and there is no back. Right. And so when you add the last element, the new element to the queue, you have to adjust this front and back. Right. Now, when you have at least one element in the queue, right, the only thing you have to adjust is back. Right. A new node gets added, so I want to make back refer to the new node. Right. You don't have to adjust front. So there's a special case when you enqueue into the empty queue. Right. So if the queue is empty, right, then the front node is also n, right? The back node is always n, right? The new back node will always be the new node that you're going to add into the queue, right? So this back always gets updated. The size always gets updated, right? You have to remember that if the queue is empty, you also have to adjust the front node, right? If you don't do this, right? So if you forget that you have to do this, then this dot front is null, right? So when you go to dequeue the queue, you end up with an error. Now, notice what happens when you make the new node, right? So I make the new node, and then I need to hook up the last node in the current sequence. I need to make its next field point to the new node, right? So the last node in the current sequence is this dot back, right? So I need to make it next field point at the new node, which is back here, right? So that's the current back node. I need to make its next link point to the new node that we're going to add, right? And so back here, right, you might say, well, there has to be another special case, right? Because when I have one element in the queue, right, front and back I have a front reference and I have a back reference, right? So if I'm always adjusting this dot back dot next to refer to the new node, but I only have one element in the queue, do I not also have to adjust this dot front dot next, right? Because back here, right, when you have one element in the queue, front and back are both, I've got two references to a node, right? I've got a reference to the front node, I've got a reference to the back node. So do I also need this special case, right? And the answer is no, you don't need this special case, right? And the reason you don't need this special case is because of the fact that Java is using references to hold its store its values, right? So back here, right, when you've got one element in the queue, right, you've got a field called front, you've got a field called back, but remember the references, so really they're pointers. They're both pointing at the same node, right? So here, front and back both point at that one node. So if you adjust back dot next, then that's the exact same thing as adjusting front dot next, because what you're really doing is you're adjusting the next field belonging to that object there, right? So that special case there is in fact not needed, right? So you can strike that, right? And you really only need the special case where the queue is empty. DQ is straightforward. There is again another special case, right? So going back to DQ, do I have a DQ picture here? I don't. Okay, so we're going to DQ the queue, right? The elements come off the front, right? So when you DQ the front element, it comes off, you adjust front to point to the next element, right? And so we're in the situation here. Now, if I DQ this queue, front comes off, you make front point at the next element. So you're in this situation here, right? Notice that you're always adjusting front when you DQ, right? Except when you get to the case where you DQ the stack that has one element in it, right? When you DQ this, right, both front and back need to be updated, right? Back needs to be set to null so that it no longer refers to a node, right? Front needs to be updated so that it also no longer refers to a node. So if the queue is empty, throw an exception. You can't DQ an empty queue, right? Otherwise, it's the same thing that you do for a stack, right? You remember what is the top element of the stack, right? So here I remember what is the front element of the queue because I want to return that element later on, right? I need to adjust front, right? So I need to make front point at the next element in the sequence. So front now becomes this front dot next. I then adjust the size of the queue down by 1, right? And then finally, after I do that, the queue is empty, right? And so don't forget, update this dot back so that it points to no null. So it points to no node, right? If you don't update this back, you end up having a reference to the old last node, right? And if you never use your queue again, that last element never gets released. The memory for that last element never gets released. Right? It's important to remember to adjust to set this back to null when you actually have no elements in the queue. Okay, so what have we gotten here now with a node-based queue? You've got an enqueue operation that happens in O1 time. That's great, right? You've got a dequeue operation that also happens in O1 time, right? Now remember, for enqueue in an array-based queue has worst case time big O of n, right? Every once in a while, you have to resize the size of the array, which involves copying all the elements from the old array into the new array, right? But if you actually look at the implementation of enqueue and dequeue, right, they are a little bit more complicated than the implementation of enqueue and dequeue for an array, right? In particular, right, allocating memory for a new node, while it's not expensive, it's not free either, right? You've got a new allocates memory for an object, right? Then you have to run the constructor for the node. You've got to adjust, the constructor has to set a bunch of fields, right? Then you've got a bunch of a special case to deal with, and then you have to update some stuff. So on average, right, whereas with an array-based queue, you just compute the new index and set the element in the array, right? So on average, the average case runtime for an array-based queue is a little bit faster than for a node-based queue, right? And the same is true for DQ, right? The average the average actual speed of a DQ for a node-based queue is going to be slightly slower or similar to an array-based queue. All right, so that concludes the discussion of how to implement a generic queue, both with an array and with a sequence of nodes. Okay. And so eventually we're going to talk about a list, because in Java you can for lists, it doesn't make sense to implement a list using a list, so we're not going to do that, right? But we will implement a list using an array, and then we will implement a list using a linked sequence of nodes. And then we're going to create an iterator over both of those kinds of lists. Right. So the iterator part will be new for you. The implementation of the list, I think, will be a review for most of you. But before we do that, I'm going to take a slight detour and tell you about generic methods. So I've shown you how to implement a generic class, right? You've got a class. One of its parameters is the type. Typically, you're going to do this for some sort of collection, right? And so your element type for your collection becomes one of your parameters for your class, right? It's possible to make a method that's generic in Java, right? So the class itself doesn't have to be generic, but you might want to write a method that is generic. So a generic method is a method that has its own type variables, right? Now, when you implement a generic method, its type variables are different than the type variables belonging to the class. Right. So in other words, you can have a generic method inside of a generic class, right? And they can both use different types, right? Their type parameters can have different names. That's a little bit complicated, especially to introduce this concept. So for simplicity, I'm going to make a generic method inside of a non-generic class. So you only have to deal with the type parameter for the method. So you can have more than one method that's generic. Every time you define a generic method, its type parameters are independent of all the other methods, right? So in other words, the scope of your type variables is confined to the method itself, right? So it's similar to the parameters of a method, right? The parameters for a method belong to the method. So these generic methods, they show up usually as utility classes that operate on generic types, right? So there's a bunch of these things in the arrays class. Right, so you have generic methods. So you have methods that operate on arrays where the element type of the array is a generic. Collections is the set of methods that operate on lists and sets. We know that lists and sets are generic, so the methods are also generic. Right, and then there's a class called Big O objects, which also has some generic methods in it that operate on plain old objects. So what does a generic method look like? It looks like a regular method, right? Except you've got these angled brackets and a type parameter inside the angled brackets hanging out somewhere. Okay. The placement of these goes before the return type of the method. So we've got stacks and queues now, and they're generic. So we might as well try to do this by creating a utility class that operates on stacks, right? Remember, our stack class only has push and pop. Right, and you can imagine that someone using a stack might want other methods as well. And so you can provide those additional methods using a utility class. Right. So our current stack class and our interface does not have a method that clears a stack, right, removes all of its elements. In retrospect, it probably should have such a method. Right. It kind of makes sense if you have a collection of stuff that you also want to empty the collection. It's not in our interface yet, and it's not in our class yet. We can add such a method to an additional class, to the utility class, so that people can have this functionality. Right. Now, if you think about this method for a second, all I want to do is get rid of the stuff in the stack. Right. I don't actually care about the element type in the stack. So our utility class is going to be called stack with an S, so stacks. Right. This is a common pattern in Java. Right. There's array with an S, so arrays, there's collections with an S, and so on and so on, right? Now, if you ever see a class that's pluralized, it's probably a utility class. Okay, so I want a clear method. Right, now remember, the class itself is not generic, right? So there's no generic type up here. Right. The methods in this class will be generic. Right. So my clear method is able to take a stack, any type of stack. It doesn't matter how it's implemented, right? And it doesn't matter what the element type is, right? So my generic type for the stack appears here. So let's just stack T, right? Remember, this T is just a placeholder, right? Someone calling the method will either provide the type here if they have to. Normally, you don't have to, right? But whoever's using the method knows that they can pass in a stack of any element type. This method will work. Right. Now, because the T appears here, right, as a generic type, and it does not appear up here, right, it means it must appear here. So now you have to mark this method as having its own type parameter right there. So this now is what a generic method looks like, right? If you look in the collections class, they all look like this, right? There's some one or more types hanging out here, and those types also appear in the parameter list. Now, how do you clear a stack? You just pop the stack until it's empty, right? So while the size of the stack is greater than 0, pop the stack. Right? We don't care about the return value from pop because whoever is using this method doesn't care. They just want the elements removed from the stack, right? And away you go, right? So there's an example of a very simple generic method, right? The only thing that changes here is the generic type shows up here. Okay, so what about you might wonder why we have to specify the type here, right? T is never used inside the method, right? So if you notice that, that's great, right? There is a way to deal with this, right? So there is a way to mark this method as being generic without actually having to write T, right? So for now, we'll just ignore it. And if I don't remember, I'll come back and tell you how to deal with it. Anyway, there is a way to deal with it. Okay, so what else might you want to do with a stack, right? So someone might have a collection of stuff, not necessarily in a stack, right? So they might have a list of stuff or a set of stuff, and they might want to push all of those elements from the list or set onto the stack, right? Inside this method, when you implement this method, obviously you want to change the stack, but you don't want to change the collection that the elements are coming from, right? So if someone hands you a list, and they tell you, hey, put all the elements in the list onto the stack, you don't empty out the list, right? You just iterate over the list, add the elements to the stack, right? It doesn't matter if it's a list or set. You can write the exact same method, and it will work for either any list or any set. Now, unlike the clear method, here, the type of the elements matter. Right, so type safety actually matters in these methods, right? If someone gives you a list of integer, you can't push those onto a stack of strings, right? So here, the type really does matter, right? The type for the collection has to match, maybe, the type of your stack, right? Notice the question mark here. All right, this method. This is a good attempt at this is a good first attempt at implementing this method. Okay, so again, the method's going to be generic, right? Because I have a stack of some element type. I also have a collection of some element type whose elements I would like to add to the stack, right? Because the generic types show up here and they don't show up here, you need a T here, right? You also need the generic type there in front of the return type. Implementing the method is dead easy, right? This is a collection, right? Collection implements iterable. So you can write a for each loop over the collection. It doesn't matter if it's a set or a list. It doesn't matter what kind of set or list. This will work. Right? Notice that's the power of interfaces and inheritance in Java, right? Or in object-oriented programming languages in general, right? You can create very, very general methods, right? That work no matter what type of collection you push in, you are starting with, and no matter what kind of stack you're dealing with. This gives the users of your classes extreme flexibility in what they can do. right? Give me a hash set, give me a hash set, give me an array list, give me a linked list. It doesn't matter, right? We can add those elements to that stack here, right? How easy to write? Well, you just write a little for each loop, right? So for every element T in the source collection, right? Push the element onto the destination stack. That's it. It's type safe, right? The compiler will only let you call this method if that type there matches that type there, right? It's type safe, it's generic, works for any collection type or any stack type. We're going to come back to, I think we're going to come back to this a little bit later on. One or two more. There's a pop all method as well, right? So imagine you have a stack and the user wants to take all the elements of the stack and now put them back into a collection of their choice, right? So you might have a stack of stuff. They might want to put it into a list, into a set, sorry, to remove all the duplicates or something like that, right? So pop all simply pops all the elements off of a stack and sticks them into a collection, right? Why is this here? This is a copy and paste error. That doesn't matter there, right? I guess this is trying to tell you that you're not going to remove the elements from the collection before you add them. So you're not going to, if someone gives you a non-empty collection, you're not going to clear their collection. Again, type safety matters here, right? If you have a stack of string, you don't want to try to add that to a collection of integer, right? So again, the element type of the stack must match, again, notice the question mark, the element type of the collection or array, right? You could write a similar method for arrays. So pop all takes a source stack, right, and adds the elements, pops all the elements off the stack, adds them to a destination collection, right? How do you implement it? Well, it's easy, right? As long as the stack has some elements in it, right? Pop the stack, right? That returns the top element of the stack. Add it to the destination, right? Collection says that every collection has an add method, right? So whether this is a set or a list, this method just works, right? And again, very easy to implement. It looks like there's going to be one more because there's space at the bottom here. Okay, so another method that's missing from the stack class is a contains method, right? So does the stack contain an element of some kind? Typically, you wouldn't do this for a stack because the way you're supposed to use a stack is to only look at the top element. However, right, if you wanted to search a stack, you can do so. The problem here is that it's super inconvenient to do this inside of a utility class, right? So we're going to do it here, but if you really wanted contains, you shouldn't put it here, right? Put it in the interface, make everybody who implements the stack implement contains as well, right? It's really inconvenient here because inside the utility class, I don't have access to the fields of the stack, right? So I don't know, is the stack implemented using a list or an array or a linked sequence of nodes, right? Because the way I'm going to search all of those things is very different, right? So instead, if I'm outside of those classes, I'm stuck using only the methods in stack, right? Which means I'm stuck only being able to push and pop elements from the stack. So how do you search a stack if you can only push and pop elements from the stack, right? Furthermore, you don't want to actually change the stack permanently, right? You just want to know is an element in the stack, right? I guess I should stop because I'm not going to get to it, right? So we're at the end of the lecture. So we'll look at this implementation in the next class. I want to tell you how to, I just want to quickly jump ahead to see if I actually tell you how to deal. Okay, so at some point, we're going to come back and deal with these question marks that are in the slide. Right, notice here, there's a question mark here, right? Do those element types really have to match, right? And so we'll see what the answer is, I think, in a later lecture. All right.